So, good, good morning, everybody. I hope everybody had so far a good conference. And if you went to the social event yesterday, the Accu boxing, you hopefully enjoyed that. I want to talk about processing decimal values. This won't be about the implementation of any of these things. It's only telling how the implementation internally kind of could look like. And it's basically all school math. So it's actually nothing really complicated. However, I work in finance, an area where I think we need to process exact values. So decimal and humans like decimal values. So I think this stuff is reasonably relevant. And it may be a nice reminder to everybody what the problems are and why we do any of that stuff. So, okay, this is basically the same slide. So my objective is actually not particularly ambitious. What I want to achieve is that I can correctly process decimal data, which primarily means if I get decimal value into the system, I do whatever I do with the system, store it, distribute it, something. Eventually, if I get the value back, it's still the same value. That seems to be fundamental, but it's not necessarily an entirely given because of reasons, and I'll talk a little bit about these reasons. And on top of that, if we get that straight, I want to do something slightly more ambitious, but still not massively so, and that is I want to do correct basic math. And even for this correct basic math, I go and say, right, sometimes if we have a fixed size representation, we cannot necessarily represent results always exact because of fixed size. We may overflow, we may underflow. So we may have to round things to fit into the fixed size representation. However, if we do so, I want values to be at least correctly rounded rather than incorrectly rounded. Okay, something which is should have been rounded up is going down because it's just hit the 0.5 and not quite right. And otherwise, ideally, things like addition and subtraction should be exact unless I run out of digits. And I will, on the next slide, talk a little bit about where the new digits come from. And multiplication should also be exact. Division, in general, can only be exact if you have an infinite size representation or an arbitrary size representation. And you can basically represent an numerator-denominator thing. Fractional powers, for example, the only way to represent them exact in general is actually symbolic because the power basically produces potentially infinite amounts of digits. So they generally can't be exact to start with. However, if we do process them, maybe rounding is a thing. I'm not going to talk about any of the power stuff or things because it's largely not really relevant to anything I'm doing. And with division can be exact, but only in very constrained, conditions. So, just a brief note on the number of digits. So number of digits can grow under arithmetic operations. And basically, if you add two values, you may get an extra digit. You may not get an extra digit, depends on the value, but you may overflow the number of available digits in any fixed size representation. If you have an arbitrary representation, you probably won't overrun unless you run out of memory, which with available memory nowadays is not that likely. It's way more likely to run out of digits with multiplication, because multiplication doesn't just add in extra digits once in a while, but pretty much produces the sum of digits used in the original together. So this grows relatively quickly. And normally the number of digits in a fixed size representation is always limited. You can only fit that number of digits, right? And you may have an arbitrary sized representation. In the end, this is also limited because either you run out of memory or you may want to still constrain it to some level, which effectively means if you want to get exact computations, the number of digits needs to be controlled in some way or the other. And often this comes out of the application, for example, in the data, in the work I'm doing, which is basically processing real-time data, getting lots of data throughout the day. They are all kind of in the same range. They may differ a little bit on the number of fractional digits, but all in all, they have the same size within the same time series. So if I add all of these things up, for example, or add and multiply with an integer, I get all the same number of digits. So there's reasonable controls we don't run out if we have a reasonably sized thing. So where's the problem actually? Here's a problem, 0.1. This looks nice and simple, and actually, what can possibly go wrong? This is clearly a finite size representation and all of that. The problem is that we in computers think quite differently about that number. If you have a double, the computer actually doesn't really think 0.1, but it thinks, all right, well, I do a different number. If it's double, it's probably this number. If it's float, and I will stick with a float going forward because it's slightly shorter, it's this number. One thing to notice over here already is, oddly enough, the double is a little bit bigger than 0.1. This one is a little bit smaller than 0.1. So there is some error. And the computer really doesn't think in terms of decimal representation of that number. It's actually just a sequence of bits with a binary power, in this case, -4. And whether it's bigger or not depends essentially on what were the last digits in front of that, and does it round up or does it round down. So the problem effectively, first off, is integers do not have a problem. We can represent integers exactly independent of the base, as long as we choose a base in positive integer bigger than 2. Sorry, bigger or equals than 2. We could try to use 1. This is what we do with our fingers, a unary representation of the counts, but this is not that useful. But integers don't have a problem. And this is quite fundamental to the approaches how to deal with decimal data as well. For fractional values, we normally, or the typical representation on a computer, which I showed before, is actually a floating point representation. That basically is the representation used in hardware, and hardware typically uses a binary floating point or variation of a binary floating point. There's some hardware, or used to be some hardware, in particular the IBM 360s, which actually didn't use binary, but they use hexadecimal. But this is basically similar to binary, just that you move in units of 4 bits instead of 1 bit. And a binary representation cannot possibly represent all decimal values exactly. This is this falls out of relatively simple math. I'm not going to go over this proof, but it's actually something like a 4-line proof. And then another problem of that is if you go, but normally I don't see a problem in my computer. Yes, this is true. If I speak to the computer and say, process 0.1, the computer goes, oh, right, yes. He surely meant this other value. But let me respond with 0.1 back anyway. So there's a little bit of magic going on over there to turn the exact value the computer internally holds back into the 0.1 we kind of expect. And this is masking the problem quite effectively, because in a lot of cases, we get back what we expect, although the value is actually wrong. The problem is, in this case, not with simple values which has just 1 digit. You cannot really produce an issue over there, however you encode it. But if your encoding gets close to the number of digits you can represent, it's very easy that somewhere something goes slightly wrong, maybe after an addition, it's slightly rounded off, and then the last digit flips into the wrong direction. And if you use too many digits, and we'll go a little bit about what that means later, then the last digits is easily wrong anyway. So my personal expectations are actually nothing esoteric. Like I would like essentially basic math like these three expressions I have on the slide hold true. Turns out none of them holds true in either decimal or float because they're just wrong. Admittedly, for single-digit fractional values, that you need to pick a little bit careful. You cannot just use 0.1 plus 0.1. This actually is the correct value because all what happens over there is it increments the exponent and this doesn't round anything off or something. So that works. But if you have these numbers, for example, it actually does work or fails. So, which gets me to the representation. How do we actually represent values or fractional values? And essentially, all representation you have consists of three components plus one choice. The choice we can make is we can choose the base we represent things in. And the values of the components depend on the base we choose. The first component is relatively simple. It's just a sign, plus or minus. We normally want to have signed numeric values, at least when we process things on a numeric basis. So we want a sign. The next one is an exponent. The exponent is essentially just a scale for applied to the next component, which is an integer representing the actual value unscaled. This is an integer. It's always an integer, and this is quite fundamental. So we can represent this guy exact, then we apply the exponent and get the real value we represent. So in practice, normally we write it something like this, where we have a leading infinite set of zeros followed by some non-zero digits, or at least one non-zero digit, possibly decimal point between non-zero digits, more possibly non-zero digits, followed by eventually an infinite set of zero digits. We normally don't write it like that because it's kind of inconvenient to write an infinite amount of zeros. So we typically leave that off. And our normal representation effectively looks something like that, or this is kind of how we can see the value. It's a sum over the digits multiplied by the base to the power of some I, for positive I in this case, multiplied by an exponent and multiplied by -1 to the power of the sign. So the multiplication by an exponent can also be a division. And especially for fractional values, you can think of that actually being a fraction where the denominator is the base to the power of a positive exponent. So there's nothing magic, it's all integers. All of this is kind of exact. The only problem is if you want to stick a value into that, we may struggle. So the real representation actually doesn't use infinite digits, obviously, we just use a number of digits. And then normally we write it really like that, like a significant times the base of the exponent, possibly in a different order. And just for the special cases, the special case is an integer, which could be represented as -1 to the power of sign times significant. In practice, this is not really the representation used by a computer. They actually use a little trick to use 2's complement, but semantically, this is effectively what it still is. And then obviously the other special cases are unsigned integers, which is just a significant. In all of these cases, still the base kind of also matters. So what do we do with decimal values? Now, if we have chosen a decimal base, we don't have a problem because decimal values just encode perfectly. In practice, the default floating point representation on the computer is actually a binary representation. So we don't really represent the value because we can't in general. If we can, it's great. And there are lots of numbers where that works out, like 0.25. We can, because 25 happens to be a power, well, a negative power of 2 to the power of -2. So in practice, we basically represent the decimal value as the closest representable value. And this is fundamental for the computer giving us back the answer we kind of expect, because there are algorithms to basically say, right, if an integer stores the closest value to a decimal, we can actually recover the value. We'll talk a little bit about that in a bit. So there's also different interest in that. This happens to be quite convenient because if we have the closest value to start off, this kind of minimizes the error if you do computations. We easily get an error over there because all of the values like 0.1 we saw actually already uses kind of all the bits. And if we keep adding these guys, eventually we have 1 bit in the front and 1 bit in the back. And now we have too many bits and we need to round off. If you have the closest value, this round off happens as late as possible and kind of effectively minimizes the error. So this is a good value to pick. And it allows round trip. So basically, if you store a decimal value into binary representation with certain constraints, essentially the number of digits you have and that you're staying in the range of binary floating point, then you can get the same value back. You cannot necessarily get the exact digits back because something like 0.10, if you input that, the computer kind of forgets about the zero. The reason for that is that binary floating points are effectively represented in a specific normalized way, and you do not really know how many digits you have. That's not true for decimal floating point, or it doesn't have to be true, and the Ieee 754 representation doesn't do that. Over there you can represent trailing zeros, which may be interesting for some application. So just to see how the encoding works, because all of these numbers were all nice and abstract, here's a way to encode 0.1 into a decimal value. So on the left we have the value of the fractional digits, and on the right we have the remaining value after we have taken out this digit. And all we do is basically we go, all right, does 0.5, is that bigger or smaller than 0.1? It's bigger, so we have a 0 over here. Same as 2.5, 1.25, and then we get eventually a 1, and then we have a remainder. Now we basically keep doing this, and we produce 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. So it's basically an infinite representation of these things. So there's nothing really complicated about that, and the computers are reasonably good at doing that stuff. So for the encoding of decimal values, when I say computers are reasonably good at that, neither conversion from a decimal to a binary floating point, nor the other way from floating point to a decimal representation is actually trivial. There's a pair of papers published in 1990, which do the conversion from an infinite representation into a fixed size representation of a possibly different base, and the other way around. They are actually quite different algorithms. The reason the decimal to binary representation is non-trivial is not so much on the smaller values, but eventually you get interesting exponents. And picking the correct binary exponent and value makes these things actually tricky. So both of these algorithms may actually use a big integer mass in on some level, which makes them unfortunately not super fast. For typical values in the typical range we use, they're normally reasonably fast, and we don't really need to use big integers for most of the things. We may use multiple word integers, but in general they are quite fast. And the original algorithm from this paper is the Force algorithm, and they're all called Dragon, so it's Dragon 4 for general printing, which has an interesting feature, which unfortunately is not exposed in any of the standard C or C++ libraries. And that is, if you give it a decimal value which encodes say a binary floating point, which encodes a decimal value, it actually recovers the value with the correct number of digits. And it would be nice if we had an exposure for that. Unfortunately, all the C and C++ versions of interfacing that algorithm specify precision and basically round to that precision. The algorithm can round correctly because it kind of knows the correct digits, but it unfortunately doesn't expose an interface, or we don't have an exposed interface to say, right, yeah, just give me the correct number of places. You can use too many places, but this has, if you want to use these things, it's just slightly annoying. There are variation, improvements of these algorithms going seemed as well, one called Risu and a recent one called Ryu. Or Ryu, I don't know how to pronounce it, I think it's a Japanese name, which do the same conversion but do it faster. Both of them are more complicated, and Risu actually internally, if it doesn't know how to, isn't really sure, actually falls back to effectively dragon form. So now the basic idea of the algorithm is actually fairly simple, right? All it does is basically it determines the decimal value closest to an encoded binary value, which also means if you have multiple decimal values in proximity, you need potentially a few extra bits of information to say whether go up or down. But the way it is, does that is actually just produces the leading digit, and it also tracks the size of the error compared to the original value. So basically it has an every time it multiplies by 10, it basically multiplies an error by 10 and compares the error against which starts out with the smallest representable value in the decimal, and it compares the error against the remainder. And if it is too small, then it stops and it knows how to round up or down. This is a basic idea. I've not implemented it because even that does get a little bit tricky once you get bigger values, because you need a big integer mass, for example, and you want to make it fast and all of these things. So the implication or the precondition for this algorithm to actually work is, however, that the binary value actually correctly represents the decimal value, which does mean that if you have done any binary arithmetics on these values, you may actually have broken this constraint already. You may have a value which is a little bit too big or a little bit too small, and then that algorithm actually doesn't produce the correct value anymore. You may have seen these values in the past where you had a value which ended in lots of nines or lots of zeros with a 1 in the end. This is essentially a version where somebody tried to print a decimal value or a non-decimal value using this algorithm. So for the round trip, just to get that straight, is you can represent the decimal value and transport it as a floating point value. Why you might want to do these things is because some programs actually only have a binary floating point interface, for example. I don't know whether that's still true, but a few years ago, at least, Accu, for example, when you had an Accu plugin, if you expose numeric values, which Accu immediately can compute with, you expose them as a binary floating point. So, but Accu always shows decimals. So you basically need to expose an properly encoded decimal value as a floating point if you want to have a predictable representation of that thing. So the obvious constraint is that you cover the correct range, so depending on where exponents are, and then there's a number of digits you can have. And I see a few questions which I may answer in a bit. So the number of digits is basically kind of the longer string where you have non-zero digits at either end. And interestingly, despite using 24 bits for float, we can only represent 6 digits for float and up to 15 digits for decimal. I will talk a little bit about why that is. In all cases, fractional zeros are lost. Okay, let me quickly answer the questions which I see. So the first question is, why hasn't there been much interest in using binary coded decimal mode in the microprocessor? The answer is essentially all the arithmetics basically need to rescale their values when you do additions. So if you have things with a different exponent, you need to shift them appropriately. For binary values, the shift is always just a simple bit shift. You basically just adjust the exponent and you shift the bits. If you have a decimal representation, you either need a multiplication or you need to have base 10 representation using something like BCD. Now we'll get to some of these representation as well, so you avoid the multiplication, but you have other problems elsewhere. The net effect of these things is that an processor implementation is actually a bit faster than a software implementation, but not massively so. When we tried, for example, on admittedly for our use cases, there may be other use cases, but for our use case, when we tried the decimal hardware implementation, which ships, for example, with Power 7 processors, against an implementation of decimal floating point in software done by Intel, run on Power 7s, the Intel software was, I think, only about 20% slower. Yes, 20% is a lot, but it's not massive. So, and in general, there doesn't seem to be a huge market to say we need fast decimal representation in a computer, in a processor. IBM tried to create this market, but there wasn't a huge pickup so far. So just on that one. Okay, and then there is the other question is what you think of the Intel math library. This library used by MongoDB to implement big decimal. So I don't know much about the Intel math library. What I do know about is the Intel decimal floating point library, and this is, for example, what we use at Bloomberg to encapsulate effectively which is used as for the implementation for our decimal floating point class. So it's actually fairly good and very fast. There are other decimal floating point implementations implementing the Accu 754 standard, but they are actually slower. So this one is actually great. Okay, and then the other thing is why Dragon, an acronym? I don't think Dragon is actually an acronym. I think it's the idea is if you process values, there be dragons. This is, I think, the concrete statement. So I don't think Dragon is an acronym. Okay, so that's for the questions. So getting back to the number of digits, there's frequent discussions I have where people go and say, "Oh right, no, it's fine. I can stick 7 decimal values into a float." This whole 6 thing is nonsense. I've tried it. Well, turns out this is actually not true. So why can't float round trip 6 digits? It uses 24 digits, right? And if you make the math, it's kind of all right. Per 3 digits, I need 10 bits, right? 10 bits can represent 1024, which is easily representing 3 digits. So we have 2 times 3, and then we have 4 digits left, which can easily represent an extra digits. Unfortunately, the values are not evenly distributed. And there are cases where they are kind of unfortunately distributed, and you actually run out of space. One example, which I actually just found, admittedly, I couldn't construct that. I found it by basically brute forcing and finding values in a reasonable range, which have a problem are these 2 values. So if you take the values on the bottom, 9.536745 to the power of minus 7, and kind of the next value of that, you actually get the same binary representation, which is just this thing. To show you, by the way, how to do some of these things, if you play around with these things, there's a great Ieee 754 analyzer. There are multiple variations of that. I normally use that because I can remember to find it using Ieee 754 and Babbage. This is all I enter, and then I find this guy. You can enter you should be able to to enter hexadecimal values. Okay, great. This is the typical case of going wrong. But over here, you can actually see that using these values from the slides, this is actually prepare E minus 7y. It doesn't have me. Oh, no, it is not an hexadecimal value. So it basically does this conversion. It shows you the normalized value. It holds internally in all the representations, and over here can play and change the value to just have a 6, and you will see that it has still the same representation of that thing. So these guys have just 7 digits. They're absolutely in range, but they have the same representation, and the computer cannot decide which one did we want. So we cannot recover 7 digits. Okay, let's go back to the slides. And I see a question from Victor. What would be a performant approach to safe numerics? I guess the safe numerics refers to correct decimal computations. I will get to that in just a bit. This is part of the presentation. So, all right. So now that we have that out of the value, how can we actually do it different? And the obvious difference is different approaches. I already hinted at that as instead of representing binary values as decimal values as binary, we just represent them as decimal. So things like subtraction, addition, and multiplication can absolutely produce exact results as long as they don't overflow digits. Comparison, formatting don't really need complicated algorithms either. This should be quite easy. And decimal rounding, if you need digits, you actually know whether the last digits is a 5 or not, or a big 5 or bigger or smaller, and you can just round easily. So there's actually no complication if you use a base 10 thing. And there are variations of doing that. And all of these things are used in some shape or form in production systems. The first representation, which we are all familiar with effectively, is using a string. I go, well, I'm not using a string inside a computer. Well, not necessarily inside the computer, but kind of on the interface. And this is kind of starting to get inside the computer. If you have a JSON file, it typically represents all numeric values as a string, or if you have fixed, this is basically text-based representation, there are strings in there. So it's just a usual representation which gets converted either to a decimal or binary representation inside. A slightly more compact version, which is used by apparently some databases, at least was used in some databases in the past, but I think it still is used as BCD, binary coded decimal. The idea over here is that each digit, each byte can actually represent 2 digits, because you have easily 16 values with 4 bits. So we have 2 of those. We can make it a little bit more compact, use less memory. And less memory is good, because if you need to compare things, you just compare these strings. So you compare half the number of things. So there are some problems with that, which are also advantages to some extent. It's variable size. So these guys being variable size means addition basically never overflows. You can keep adding, and you just increase memory, and you never run out of space. Multiplications, because you all the time get bigger values, you may run out of memory over there, but probably doesn't overflow over there. However, a variable size representation is a problem if you store things in a database, and you may actually get a relatively large representation even for small values. And the other thing is computations on these guys are relatively slow. Basically, process them digit by digit. You can do some tricks and do SIMD operations on these things. We can actually represent them as in bulk. It's still not as effective as integer operations. but it's certainly a representation for decimal values. Not super fast, but entirely doable. So the next one, which is popular for the people who want to do fast, is a decimal fixed point. Now, what's the idea of a fixed point? It's basically, well, the scale we have, we don't necessarily need to have a variable. If we know what ranges we have, if we know, for example, we process pounds or dollars, we know there's only 2 fractional digits. So we could just go and say we represent our value actually as an integer, and we interpret when we look at the integer to say, that's a decimal point to place it in. Which basically means all the operations are really fast. They're actually faster even than binary floating points, because they're just integer operations, which are really, really fast. So this is great. There is a slight disadvantage, and this is you kind of need to know the scale, and the scale is fixed. Well, you can make it flexible. I get to that on the next slide, but knowing the scale may or may not be a problem. If you know your scale, go with fixed point. It's absolutely the right choice. If you need to process a broad range of different things and you don't know the scale, this may be a problem. Whether it is a problem depends a little bit on context, but if you have a system where you have multiple components looked after by different people, any implicit knowledge is a problem, and then the fixed scale becomes quickly an issue. There's a small other thing, and then that is if you do computations, if you do multiplications, and you have actually 2 fixed points and you multiply them, you get a fixed point with sum of the digits. There is there were some proposals to the C++ standard library which talked about fixed point. There were actually binary fixed points, because there are interests in binary fixed point, I think, for usage in color scale processing, for example. And they would actually use different types as a result of things. So they would actually, even for addition, accommodate that you get an extra digit potentially, which makes the computation a little bit odd, but it's all workable and it's fast. The speed of these things is definitely an advantage. Now, maybe we don't really want to have a fixed point. We could think, well, it's just an integer. We could just take the scaling factor kind of out. And operations between these things are still relatively simple. If you have 2 fixed points, one with n, the other one with m digits, you get a fixed point with the maximum of n plus m digits. On addition, well, maybe plus 1. Unfortunately, this already, if you do mixed fixed point operations, that's already an issue, and this already requires a multiplication by a power of 10 or division by a power of 10. And well, if the constant scale factor is not known, which is like in our system, I process market data for all kind of sources, and some of them have actually only integral values, so they have 0 fractional digits, and others have up to, I think, 8 is a not uncommon number of fractional digits, so there's a wide variation. And unfortunately, the values, if you go and say, well, but all of that fits, if you have a 64-bit integer, you can effectively fit in 19 decimal digits, 19 or 18, I'm not sure. And unfortunately, if you use 8 fractional digits, the upper end gets reasonably close to things like military budgets or government debt, which are roughly in the same order, and you're already really close to these things. It may work, but there's not much space. And if you have a little bit of inflation and you get some country where the numbers are bigger, then you run out of space. Maybe we could just go and say, well, we basically don't encode the scaling factor into the type, and we just have a flexible, and it comes from context. This is actually what people do on exchanges. I know that. I've worked in a space where they get data from exchanges. They basically tell you at the beginning of the day, the values on this instrument are scaled by this factor, 10 to the power of 3 or 2 or 4, whatever it is. And then throughout the day, you only get integers for these values and you scale them with that other value. That does work as long as you don't have too many parts of the system involved. The moment you start storing these things into a database, for example, and the scale change, you have a problem. So if you store things in a database, you definitely want to know the scale together with that. So, and knowing it from context may work for a high-speed trading application where you basically go, right, I want to trade on this instrument, and you really set things just up effectively doing an integer, and you basically just want to do bit operations on these things. It does work. Effectively, it is a decimal fixed point where the type is not encoded necessarily, or say the scale is not encoded in type. It can be done, but only localized. So what about the following idea? Well, we take the fixed point thing and we just store the scaling factor in it. That's just a brilliant idea. It should be fine. Well, yes, has a name. It's called decimal floating point. This is basically nothing else than the same thing as a fixed point thing, but instead of having a fixed scale, we just use a variable scale. The representation is effectively similar to a binary floating point. You have these three components, and you basically encode them kind of in a bit field-like thing into an integer. In practice, you don't use bit fields because it's slow, and there's also the thing. In Ieee 754, they had the brilliant idea to say that if you actually use all 16 digits, the first digit only uses 10 values out of the 4 bits we have over there. Maybe we can use the other values, and there's a little bit of interleaving. So basically squeeze things in and you get an extra exponent out of that. Well, great. Unfortunately, that makes processing a little bit slow because you always need to decode these things. But on the grand scale, the actual problem of this processing is not so much the decoding of the values. There's effectively just bit operations. The real slow operation is basically on addition, making sure the exponents are the same, and if they are not shifting them. Conveniently, if you have values which are all on the same scale, you don't need to shift them because decimal floating point don't benefit from not storing the implicit 1 in an as you can do as for binary floating point, and which is done for Ieee 754 binary floats. There's an implicit 1 at the beginning to say, right, well, the first digit is always 1. This allows us to not represent that. So the binary representation actually uses a 24-bit significand using a 23-bit representation. This is for the normal values, and then you have denorm values. Once the exponent goes too slow, the first digit is actually considered to be 0, and you get these other values. But this benefit you don't have for decimal values because you wouldn't need more bits anyway. Instead, for decimal values, you may want to actually represent the number of digits you actually have, which may include trailing zeros. Although the value of 0.1 and 0.10 is the same. If you compare these two values, they are the same, but they can be printed differently, which gives you potentially extra information. Let's say if a time series from maybe different exchanges, there's different number of digits quoted. So you can actually see, all right, these guys actually quoted 2 digits, and this guy quoted 3 digits, but with a trailing 0. So they could have gone a little bit bigger, a little bit smaller easily. So this is the decimal representation. What is normally used in practice, or what we use in practice, is the 64-bit representation of decimals, which basically uses 54 bits for significand, giving you 16 digits, which in practice is sufficient. Even for things like government debt to represent that reasonably accurate, you normally don't represent many binary, fractional values of that. You get 9 bits exponent, which for financial applications hopefully stays correct. Otherwise, we have massive inflation and we run out. There's quite a bit of space over there, and 1 bit sign as well. So the The key problem on these things is if you add them or subtract them, you may adjust them. So, which basically does require, in some cases, you get away with multiplication. This is okay, but sometimes if you have produced too many digits, in the end, you may need a division as well. And divisions are actually hideously slow. Especially these divisions may actually have produced more than a 64, or like a multiplication may have produced more than 64 bits. You actually have a multi-word operation. And a multi-word division is even worse than an integer division, which is already bad. So it's actually an interesting idea. And that is, if you need to rescale these things, you can actually replace a division by a multiplication of integers. This seems odd, but let me quickly go over the basic math of that. That's kind of, well, I mean, nothing is super surprising over here, right? So if you have a division A divided by B, we could obviously write that as A times 1 divided by B. Okay, this is just rewriting things. Now, if you scale A divided by B by 2 to the power of n, multiplication or division by powers of 2 is fast. So we can actually arrive representing B or representing the factor over here as an integer, and then the result we need to divide by 2 to the power of n. Now, the final realization is eventually we will need to trail off, and if we round down the value, we actually still get the correct value of the division. So the basic idea is to actually compute an integer, which is 1 over b, scaling it by 2n, and basically storing that value potentially, unless you can produce it reasonably quickly on the fly. Doing this was doing the division, then multiplying the set guy, and then just shifting digits. If you have something like a decimal floating point, where your b is effectively an integral power of 10, you actually don't have that many b's you need to store, because I think you get away easily with 32, maybe you need 64 of these values. But this is reasonably doable. Now we trade memory for computations, and as far as I can tell, this small amount of memory still pays off compared to the multi-word multiplication you would have otherwise, especially if you don't really have that many values. Also, I think the powers of 10, you can actually kind of produce, if necessary, on the fly as well. So this is the basic idea to actually make multiplication, make these operations faster. Okay, so if you want to use something like decimal floating point, like for fixed point, there's not much to say. There are different implementations of that, I'm sure. I'm not using one, so I'm not recommending one. And it should be relatively easy to knock off. It's just an integer. These are all just integer operations. Decimal floating point is a little bit more involved, and there's basically the inter implementation, which is unfortunately a C implementation. You can use that, but it's actually a little bit fiddly to use if you want to write relatively simple expressions. So it makes sense to encapsulate that into a class, and there's such a class open source called published by Bloomberg as part of BDE. So there's a link over here. The class itself is called BDL-DFP decimal 64. It's just a namespace. There's also a decimal 32 version thereof. The computations on 32 bits effectively convert the 32-bit into 64, do the computation and go back, roughly speaking. And there's also 128-bit version, which you could use, but this is slow. And in practice, I'm not aware of anybody using it. The reason they do the conversion to decimal 64 is internally, they actually do use some tricks using doubles as well. haven't quite understood how that works, but they have papers and discussions on why that is correct. So this does exist, and which is pretty cool. Okay, so there's one thing which is interesting. Now, if you convert from a binary to decimal, and whether it's binary to decimal floating point or actually to string, there are two choices you can do. You can either go a fast route. The fast route is basically saying, all right, I actually want to represent the binary value I have as closely as possible in the decimal value. So the reason you may want to do that is the binary value may be the result of an estimate and of any shape or form, or maybe it's an interest rate or something. And you actually want to get rather a value as close to that value, in which case you can actually convert them fairly quickly to decimal without doing any of that drag and force stuff. Or you may want to restore a decimal value, which was stored in a binary floating point. Like, this is almost certainly what Excel does. When they get a floating point, they assume, all right, this probably stores a decimal. Let me convert that correctly so that we present the correct numbers to our clients. This is slow, but gives you back the original decimal value despite having been in a binary floating point. So there's a choice of two operations. For the decimal 64 class, we basically stuck with the idea we do the same as we do for conversions otherwise, and that is the implicit, I don't think it has an implicit conversion, but if you just cast the value, you actually get the fast computation, which may be a bad choice because people may be tempted to do that. But the other operation is significantly more expensive, so we basically made it explicit. Okay, I see a question for these things. So how many significant figures are available in IEEE 754 DFP? The answer obviously depends on how many, whether you use a 32-bit, 64 and 28-bit version. In the 64-bit version, it's 16 digits, basically using 54 bits, roughly speaking, with the top word or top nibble being used to interleave an exponent. That's basically 5 times 3. That's basically just, or you can represent them, and there's actually two different representations. One actually chopping things up into 10-bit units. This gives you 15 digits and then one extra digit with special handling. I don't know what the values for 32 bits are for sure, but I believe it's actually 7 digits for decimal 32, and for 128, I have no idea. It's I think off the top of my head, something like 34, 38 or something like that, but I would need to look that up. So this answer, and what would be another question? What would be a performant approach to safe numerics? Oh no, sorry. This already answered, I think. Okay, cool. So let's carry on with things. All right, so conversions, and then the next thing we have is sometimes there's a choice: decimal or binary. Should I use always decimal, or should I use always binary, or should I use the mix? The answer to that is unfortunately it depends, right? So if you have exact computations like additions, subtractions, multiplications, ideally multiplications with an integer, probably you want to have a decimal representation. So if that is your goal, decimal is the thing. It's slower, but it's correct. Now, the reason we have binary floating point is mostly because we want to actually do estimates. We want to simulations. We do like all this machine learning stuff is basically floating point maths. You don't want to do that in decimal. It's just slow, and you're not interested in the exact result of these things anyway. same with simulation. Simulation is kind of, yeah, so many inputs, you have no idea what the outcome is. Some of these things are even randomized. So whatever, you clearly want to use binary values over there. It becomes a little bit more interesting if you do things like a fractional power of something. Now you have exact values, both the let's say the interest rate you have and the your credit or debt. Times the interest rate. Well, over there, you probably want to do the computation in binary because this is just faster. And then the result is something which is an inexact value anyway. You cannot represent or you won't get the exactly correct value. So you could choose to say, right, I stick this binary over here. There are reasons to stick them back possibly into a decimal value. That is, there are actually rules about rounding of these values. So basically implementing these things and giving back a decimal value, which is correctly rounded and all of these things, may be an advantage over there as well. So it's not a clear cut, all right, use this or that. You need to choose what is the right thing for the application. And unfortunately, decimal is correct for some operations, and the choice does involve a little bit of slowness. So when I say a little bit of slowness, if you only look at the computations being done for the things we looked at, which is basically computing something like a total value for things traded on an exchange, which effectively is multiplication of a decimal value with an integer and summing these guys up. And essentially, the exponent is always the same, so there's not a lot of shifting around. They may be different for some objects. So sometimes there's a little bit of shifting necessary. The slowdown for these things, which we measured, was about 6 times slower than doing the binary stuff. Now, 6 times sounds, oh God, this is huge. But it's actually, this is just this computation. Normally, the processing around all these things, maybe it's storing things, distributing things, figuring out what this is, takes also quite a bit of time. So the overall slowdown is actually not that big. It's just benchmarking the floating point operations. All right. So yeah, to just actually finish things off a little bit early is nature was actually kind to us. Nature went kind of, all right, I give you 8 fingers, count with 8 fingers. Because this is basically a power of 2, and we would have no problem. Unfortunately, somebody had the idea and goes, all right, well, if I do a unary encoding, why don't I use sums as well? And now we have 10. So, and we absolutely need this number of fingers to play piano or keyboard or any of these things. All right, so thank you very much for listening. I hope there was something useful in here. And I think we have some time for questions, if there are any. So I don't see any questions. If you still have any questions, please find me. I'm normally hanging around somewhere on the first floor, typically trying to get to a table where there's some talk. All right, then thank you very much. And on the slides, there are some references to the resources I pointed to. All right, thank you very much.